All right. Welcome. Hello. Nice to see you again. My name is Agent Ultra, and I am here to learn about wave function collapse. We're going to be implementing it in Haskell, as we have been for the past few weeks now. Well, 5 weeks maybe. A little bit a month. Whatever. I do these streams once a week. We spend a couple hours hacking on stuff, and this is what we're working on. We're learning about wave function collapse. Wave function collapse is a procedural generation algorithm, and it's kind of built on top of like constraint propagation solving and a couple other neat little tricks. And it's a very general kind of cool little algorithm. So we've done most of the pre-processing steps now, and we started digging into the core of the algorithm last week, and we're going to continue on that journey. So yeah, come with me, learn, hang out, backseat program, talk about your projects, what you're working on, ask questions, it's all good. And just listen to the chill tunes. Let's just get settled in now. I got the code pulled up here, just make a chat, I got all you going. Let's start building everything. Back, we'll use our test runner, fast, and file watch. So we'll just rebuild and run the tests on every file change. Okay, there we go. So let's see, where were we? Okay, we're down here. We're doing entropy calculation. So this is in the little plan here, our choose a cell with the lowest entropy. Entropy is what we need to calculate. Entropy is basically used to try to avoid what's called a contradiction. So contradictions when we go to collapse all of these cells and choose, we ultimately want to collapse all the cells so they only have one tile left. But it can so happen that in the process of collapsing the cells, we come across one that has no more possible choice of cell to collapse down to, in which case we call that a contradiction. If we were to choose, I guess, the patterns somewhat randomly as I understand it, we would have we'd have increased odds, say, of encountering this situation. So by entropy, we mean choosing the cell that has the least possible remaining choices for a pattern that we want to pick for it, basically. With a little bit of extra mathy sauce on top, but that's the general gist of it. And the idea there is that we will, by choosing the right one, we will kind of make it less likely that we'll encounter contradictions, but not impossible. That's kind of a key, I guess, to being able to go to the next step would be choose one of those, and then then we can move on to the next steps like collapsing and propagating choices. That's what we're going to be working on. All right. Tile frequencies, sum of weight, log weight, and all that stuff is all good. We got the make grid stuff wired in. All right, and there's our entropy and all that sort of stuff. The next thing we need to do, now that we have the entropy calculations, we have to make grid, is we have to, when we go to collapse the cell, we cached, oh yeah, we did this caching thing. We have to update the cell's total weight and some of log weight. Let's update those cached values there. And choose a value for it. And so I think what we need is collapse the cell at collapse. Take a cell. And a cell. That would make the most sense, right? Leave that undefined for a moment. And we're going to be really collapsing these on the grid, though. Because once we collapse it, we'll want to be able to propagate out the pattern we picked to the neighboring cells. Check for the overlappings that are there, and then remove the possibilities of those things from happening. It's a bit abstract. Let me see if I can draw this out. So I think what we actually want to implement is collapse on the grid. And we'll give it a tile coordinate to collapse at. Right. Beep, 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 beep. One of these days. Get my tablet back in action. For now, mouse drawings. Oh yeah. So say these all have all possible tiles in them at the moment. And we want to pick this one. All right, so we collapse that down to a particular value. In this case, like blue circle. All right, now we have a set of adjacency rules that tell us what possible patterns overlap with blue circle. And those are the ones that we need to keep here. We need to eliminate all the rest. From here, 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 here. Right. And as we collapse those might propagate out their changes. And so the second generation, you know, it's going to go out. We're going to collapse one here. And we might even end up collapsing all the way up. But it's going to go across our grid and kind of spread out. So the information to collapse a cell at a particular place, I think, is kind of part of the grid, is what I'm saying. I think that's probably the way to go. I'm going to call it collapse at. Now our grid has coordinates like that. Almost like a 2D sort of thing. And then we have to give grid. And we'll probably get a new grid back, won't we? Now, collapsing at, do we want to do like the whole... It's also, we want to kind of do this as work up in small pieces here. I feel like I'm taking a step where I'm going to draw the whole dang owl. That's not kind of not what I want. So there is a cool tutorial on this stuff on grid bugs that we've been working from. Helps kind of understand what we're doing here. Rough sketch. Choosing the next cell. So there's our tile frequencies and caching. Right. Collapsing. Yeah, oh, okay, they took the same approach here too. You give it a coordinate. And just collapse the cell at a given coordinate. Okay. And using our frequency weights, I guess. Okay. And I think this is probably actually going to be kind of in a stateful sort of thing. So we might want a state here. Really. Yeah, so before I get into that, We'll keep collapse out for a second. Let's define a little state. A little bit of state we're going to need. What are we going to call it? We'll call it wave state. Sounds good. The wave state will have our grid. I can't type tonight. That's right. Ugh, new keyboard. I'll tell you. I ruined my old, well, yeah, I guess it's pretty old. I had a Dash keyboard too, Ultimate. It was amazing. Darth Vader, I called it. It was great. But it didn't survive me. It took about I don't know, 10 years, 14 years, 12 years, 12 years maybe. 2012 or somewhere around that when I bought that thing. And I couldn't resurrect it. I have this new one. It's not as good. Okay, wave state, grid. It's gonna be our grid. Grid. It could be a state of our wave state. Maybe it won't really return anything. It'll just collapse that cell at that point in the grid. Cell index. Then we don't need the grid anymore. Alright, so then we can get our wave state by asking for it, or get, and pull out that thing. Then we need to use our cell index to get the cell we want, which means it's going to be a lookup. Wave state grid. Now I think it's map.bang cell x. Nothing. Something there. Just cell. Oh, we don't have state imported. That's okay. We can do that. Import control.monad state. That's strict. Oh, and why is it doing that? Oh, we need grid's a new type. We got to get the cells out of that. Yeah. Get cells. I don't think we need the. Did we do? Was it not a map? It's an array? An array. Okay. Array. Right, so of course I was thinking it was a map, so we don't need any of this. If we index outside of our array, we're going to be in Problemville. Data.array. I don't think it has a safe accessor. List array, queue array. It just has. Yeah. We can get the bounds and make sure that the index is in it, and we can create a safe function to do this. Maybe array, maybe at. Some array of bounds. what do they kind of give the type? IE. And index I. And return maybe E. Then we will check that array x. We'll have to have an inbounds function. X and array. Then we can do just array thing. X. Otherwise, nothing. And then where bounds gives our I and an array IE returns a Boolean. Okay, we need to get the array bounds. And then, what can we say about I? Hey, I'm Kia. Welcome to the stream. How you doing? Thanks for showing up and watching. First time chatter. What time is it here? Ooh. It is about 8:30 p.m. Also, hello, tech support. The way functions are beginning, we're just at the verge of collapsing things. It's kind of what we're working on right now. Is getting into the collapsing part. And hello. Okay, so what can we say about I here? We know nothing about it except that it is an index. But is it in the bounds? Ooh, sounds rough, Amkey. Leap is definitely super important. Highly recommend. Yeah. I do, if you check my stream, if you check my socials though, I do back up my VODs on YouTube. And I'm on type.pl server on Mastodon here. Need this. There we go. Type.pl. That's, yeah, it does kind of get its inspiration from quantum physics. That's where I guess it's kind of the name from. It's really, in computer science terms, it's more like a constraint propagation solver, but the metaphor from quantum mechanics seems to gel with a lot of folks. Yeah, I should get better at twitching things and doing Twitch stuff. I've been meaning to like update my profile, you know, get a proper profile picture and all that stuff. You know, maybe I can get some like get someone to make me some fancy, I don't know, borders and such. Yes, please, go to sleep, have a good one. I do these streams once a week, but hopefully you can catch one sometime when you're not so tired. Yeah, so let's see. We can test maybe for equality. What is, we say index x of I, xi read I equal xi equal e, xi. What does x give us on that? Okay. Oh, we do. We have in range. Oh, nice. Okay, so we know that I has to implement x, which has in range, I think. It looks like from data.x. Or data.index. Cool. I think I'll put here. Put that here. I don't think I need inbounds, I just need in range. It returns a bool, yeah, about the shape I want. Now the only thing I have here is that I only know that I is I. We don't know that it's an X. I wonder if I can add xi as a constraint. Would that work? I'd have to import the class here. Oh, array exports it. So I wonder if I even need that. Array.x. And what can I do here? So the type error here is like giving me pretty good information. Just look at this for a second. We couldn't match the expected type. Array IE with actual type I. Why am I getting that? Alright. I here. Actually, I'm not sure. Oh, because I'm giving array here. That's why. And so I need array.bounds. No, that doesn't seem right. X. Maybe it is. Maybe it's the other way around. They just got to flip the arguments around. Like this. Yeah. There we go. Yeah. Yeah. Okay, cool. Tech support should check out types.pl situation. It's a friendly little community. Yeah, try it out. You will have a follower in me. I'm also Agent Ultra on there as well, so I'm pretty easy to find, as you know. Okay, so yeah, we don't need this function here now. Area.bang, we need maybe at. Okay, now we're back in action here. We got our two holes. Okay. So if we want to collapse the cell here, we have a cell in the array. Then we need to yeah, we need to get that cell. Seems like a logical first step. Oh, we have that cell. Sorry, we have that cell in scope. So what do we want? We want to change the cell state and put it back in the grid array. All right. We need to update. So we'll need array update. I believe it's. Is it update? We need to add that. Data.array. cells. Stocks bound. Oh, it does export range. So I don't actually need to explicitly import for data.x. For one. Yeah, this function here, I think, is our updates. We've given an association list here with our updated value for the cell, and that should give us back a new array that we can wrap back up into a grid and then pass back into the state. So let's put that part of this in. Our array is going to be on that side, so we want I'm going to want to bind that. Call it grid array, get cells, wave state grid. Or I can just call it cells. That'll be fine too. As long as there's no naming collisions. Okay, so now I have cells in scope here, so that means I can do cells array.// I need my updated here. I know what the cell index is going to be. That's going to be the first argument in this tuple. And then we need something there. And then, with all of this, I'm going to wrap that back up in a new grid. There. And then we put that back in the state. Is there a way to data.control.state? There's a put particular place the whole state. Modify S to S. And there's gets. Okay. Modify. That's going to be wave state to wave state. Which is really going to be S such that wave state grid equals new grid. Something like that. Kind of messy, but hopefully it works. Okay, so then we just have the nothing case. We can't collapse anything at nothing. So maybe we could just do pure here. Or we could return an error. Kind of meh, runtime error. We could add, like, if we were going to do monad transformers here, we could add, like, an accept T around here and kind of stack things together. We'll do quick and dirty here. And if we want to go that route, we can go that route, but really I'm thinking this is going to be kind of an internal function and implementation detail we really shouldn't be getting. invalid indices here, so I'm pretty happy with the runtime error if we do get one. And we can add a little information about the grid it was, the value it was. Oh, it's keyboard, I swear. Ah. Okay, and we'll just do the show instance on Celix, if we can do that. Yeah. Super sick, okay, and where's our other hole here? Down here. Yeah, so we need a cell now. So we gotta do something with cell. Yeah, what do we gotta do with cell? Alright, we gotta eliminate... If we're gonna collapse this one, we have to pick the pattern to collapse it to. No, we're collapsing this one. Yeah. So we have to pick one that we're gonna collapse to. And then we have to set all the other possibilities as false. And then we have to set collapsed to just the pattern index that we collapsed to, the one we picked. And then we have to update our total weights and sum of weight log weight for that cell. Alright. So we need to do a bunch of things with it. Collapse cell. That'll be a cell to cell. Leave it undefined for a moment, and then I'll pop it in there. Like that. Okay. Okay, how are we gonna pick the pattern to collapse this cell to? We're gonna need access to our frequency map. We're gonna need that. In fact, maybe that should be in our wave state. We call it frequency map, right? Frequency hints. We need access to that in our algorithm. Ah, jeez. Sorry if this happens a lot on the stream for a little while until I get used to this shoddy thing. I'm gonna replace this keyboard with something useful. It's just something I picked up quickly to replace old Darth Vader. Rest in peace, buddy. I need a big, honkin', full-size, chunky, badass keyboard that weighs a ton. Okay, so we need the frequency hints because we need to determine the available cells that we have, the possible ones in this cell, the possible patterns that we have that we could pick in this cell. We need to do the frequency hints because some of these are going to be more likely than others, as you might recall from the earlier streams we did when we were doing the pre-processing. So frequency hints are generated from the input, and as you kind of subdivide that input texture, you might find a particular subpattern in the input texture repeats or is like duplicated. And in that case, we actually just increase the likelihood that that tile will be picked in the core algorithm, right? So that's what we're going to do. That's what we're going to need here, basically. So we're going to need the frequency hints for patterns. So we're going to pass that in here. Frequency hints. It's getting a bit mer. Okay, and what else? Yeah, and then we need a function for picking it. Picking from the available things. Okay, so let's start off with that. We're going to pick a pattern index. We're going to give it the frequencies, and we'll give it the list of possible possibilities. What do we call that field? Cell possibilities, or just possibilities? Let's not leave a parse error there, so I can jump back to it easy. Cell possibilities, yeah. Okay. Okay, and assuming we have such a function, put it here. That's going to take frequency hints and a list of pattern indexes. Leave it undefined for now. That's not a skip. What did I... No. Pattern. Total weights. Maybe I just used an index. I thought I had pattern index. I use the full word, not ix. So consistent. So consistent. Okay. So there we go. Pattern ix. Pattern index. So if you have this function, well, it's an array. Okay, an array. Cool. Right. Right. So is that the problem with that? That's good. Yeah. T. Oh, yeah. We need to pick a pattern index. That'll be the return value. There. I don't know. I'm going to brain fart on that one. There we go. Okay. So then, assuming we can implement that, which I think we can, we have to fill in this hole with a cell. Now we've picked the cell that it could be, or the pattern that it could be for that cell. So we can eliminate all the other possibilities. All right. So we're going to return a cell. Pop this over here. Boss, cell possibilities. That's going to be something. So... collapsed. That one's going to be pretty easy. We know that's going to be just the pattern index we picked, so pattern X. Cell total weight. Give me something, and cell sum of weight, log weight. All right, we're probably going to, I think those holes we can fill in with the functions. Calculate the total weight, the sum of weight log weight. Alright, so we've given the remaining possibilities. Oh, yeah, we probably want to bind that. So we calculate the remaining possibilities. So we can pass it into total weight with the frequency hits, and we get a float back to pop in there. Remaining patterns. Actually, if we're collapsing this down to one value, we don't really have to do that anymore. No, we don't care about that, actually. Yeah, because it's only when we're reducing the size that we actually want to recalculate that. If we're collapsing down, we're picking a value for it, so it probably doesn't make sense to update there. I don't think we have to do anything with that. So in that case, we just have to set the cell possibilities to be just this one, and it's collapsed to this. Alright, so we keep the cell possibilities updated so that when we're doing the checking later on, that we don't reach into contradictions. Or, well, no, just, yeah, just because. I think that might be important later. Anyway. Blah, blah, blah. But these we don't really care. So we can just give, like, dummy values for them. I think that would be fine. Alright, so cell possibilities. We just have to implement pick pattern index, and we have to give a value for cell possibilities. Abilities. And that's going to take the pattern index as well. Pattern index as well, but it picked. So, collapsing the cell possibilities, we give it a pattern index. And an array, a pattern index, a bool, and we return an array pattern index to bool, bool, of bool. Pull this over a little bit so we can see it. There we go. Collapse cell possibilities. That's going to be an array down to our association list. We'll map over that association list. So we'll get the pattern index. Alright, we'll map over that with something, and then we can do the update. Array.// which we'll have to do here like this. We're going to need the input array here. Yeah, this is going to get a little messy, so we're going to break this up a little bit. I'll let bind this part. And we'll take the input array. And then here we will use I think it's maybe this way. Probably double check that. Oh, the input, the array on the left of the operator. Makes sense. Okay. Okay, so then this hole here should be, yeah, a Boolean pattern index to bool. I don't actually care about the value here. We just want to know if we need if it's kind of ugly to express as a lambda, but if the p index is the same as the one we picked as this index, then we want this x to be true, else we want this px to be false. And cell possibilities here. Oh, I just messed up the type. I just didn't type right. Okay. Okay, so that is good. Hopefully. Kind of ugly, but there you go. We could probably make that a little cleaner if we wanted to bring in another little function. Matches. And if matches will basically be this function. Let's call it keep if matches. I think that makes it a little bit more clear what it's doing. We just need px as the input. Yeah, I'm gonna wrap that up. Okay, that works. So, and then we can clean this up. And we can get rid of the lambda here. And the arrow. By bringing in px whatever over here. That works, and then we can clean this up a little more by getting rid of the if, making that a guard. Otherwise, I don't want to line it that way. That looks a little better. Okay, so we collapse all the cell possibilities down to just that one. And then we just need to implement pick pattern. Yeah. Okay, so pick pattern. How are we going to implement this one? We're going to have the array of the pattern indexes that are valid. So we'll get the list of possible patterns from the array. I'll just call it patterns. I'll actually call it the function possible patterns. I'll just keep that F and patterns or keys. Got possible patterns. We haven't really defined that. I'm not sure if it should be a top level function, so I'm just going to put it here for now. And if we find we need it elsewhere, we can pull it up. No problem. That's just going to be an array pattern index equal to a list of pattern index. Okay, so if we can get that, then we should be able to iterate over our choices. Stopping on the one with the most weight. Or we can something. I don't know if I'm explaining it well. Let's just write the code. No, I don't know what I'm going to be writing here, actually. How do they pick one? Use a random generator? No. We need a way of choosing which tile to lock in, which pattern to lock in. That's what we're doing right now. So this method will select randomly between all possible tiles for the chosen cell, assigning probabilities based on hints. Yes, that's what I assumed we wanted. Okay. So we choose from a probability distribution where possible values are the tile indices yielded by this iterator, and weights come from frequency hints. So for a given cell, the remaining possible tiles are 2, 4, 7, and 8, say. The relative frequencies are indicated by the width of the sector. So I guess in the frequency map, 7 maybe appears twice or 3 times, and 2 appears twice, say. Something like that. We want to choose a random position within this strip and see which section we ended up in. Naturally, we're more likely to end up in one of the wider sections. Okay, makes sense so far. We choose a random number between 0 and some possible tile weights. Yeah, so we do need a random integer. Hang on. Okay. If we're going to need randomness, that means we're going to need system.random, and we're going to have to put our random generator in our state. I think that might be a package we have. That might not be in base. So packages. our test. Library. Random. Stop. The builder is getting confused. View. Okay. Restart it. No, we're not. No, that means me. I'm getting confused. Oh, yeah, that makes sense. I also need to add MTL. That's better. Okay, so back to function code. So we need system.random, which means our generator state we're gonna have to keep in our wave state. Gen of int. Okay. So then we're going to need a way to call that random number generator and get a random integer between 0 and, what was it? The sum of, in between 0 and the sum of possible tile weights. Oh, that's on the cell. That's, oh, that's our, okay, yeah, that's the value we cached, right? I guess I called it some cell total weight. Yeah, I think that's what I called it. I called it total weight. Okay. Let's see. So let's we're all the way down here in pick pattern. We could pick that number before we call in the pick pattern. We're in a state up here, but in pick pattern we're not in a state. Unless we make it a stateful function. How do we use it here? We use it here. We'd have to make that a stateful function. We could make this a do. Then we could get our random number between. Zero and the cell total sum of weights. Our total sum of all weights. What was it? cell total weight. And then, I don't know, we'd have to do that before up here. Pass it into that. Something. Terrible name. Maybe it'll make it obvious when I pass it around a little bit. Collapse cell. We just pass that along. Big pattern X. Yes, feels like I should be making this a state. Since I'm threading it all the way down in here. It's all internal, but feels like something pick pattern would be able to do by itself, you know? And then these functions will be passing around frequency and just get it themselves. But then I wouldn't be able to use them. I wouldn't be able to collapse like this. I'd have to be making an action. Which actually might not be so bad. We'll see. Make cell prime like this. And the collapse cell look like this. We wouldn't have to pass in the frequency hints here. Just the cell. We wouldn't have to do that. We can just do here. This will be already collapsed, so we could just do cell prime. I can rename it collapsed cell. And be that. So then we can get rid of hints here and int here. This will be a cell, this will be a state, a wave state, returning a cell. And then this will be pure. Cell. After I do pop, 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 and pattern X could be a bound like this. Could also be a state function like that. And then we can get rid of this, that. Still maybe need the cell possibilities, yeah. And then this would be a state, wave state, returning a pattern index. That's cool. So then here we could do push this down. All right, so the first thing we want is our random number. Oh, we need the cell that we're operating on as well. Let's just pass that in. Because we need a bunch of data from it. These cell possibilities. Yeah. Okay, and then we need the random generator, says we do. What do we call? Let's see, steal their name. Random remaining. Okay, remaining. And between 0 and cell total weight. Saw. I guess they mutate that. So for each tile index and the possibilities, recalculate the weight. Or recalculate the weight. For that. Okay, and then remaining. Oh, okay, if that's greater than weight, then we take weight away from that. Okay. And then eventually we get to this branch here. I don't like that, but that makes sense. So we need to with our remaining, we want to change, and we're going to need to pull. We'll have the frequencies in there if we make this function as well. Patterns. Okay. That doesn't need to be in anymore. Go. It's going to be a recursive function. Int. The patterns would be our array of indexed view. No, whatever possible patterns returns, there's going to be the list of pattern indices. Pattern index, and it's going to be a state, wave state, returning pattern index. All remaining patterns or keys. Okay. So, first thing we got to do is get our what was it? The possible tile index. Well, the base case. That one. Ooh, Yeah, this is the error case. In this case, couldn't find tile to collapse to. Pattern. Could Couldn't find a pattern to collapse to, but we do have a P in scope. That means we can test that one. If the weight of that pattern, according to our frequency map, is there. Total possible tile frequency. Oh, relative frequency. I don't know if we implemented that. Oh, we did. Okay, so we got our hints and our thing. We call that. And get that as our weight. And then we just have a simple little if. Okay. So frequency, P, we need our frequency hints. I think frequency hints, we can just get this. Just call it hints. Gets wave state frequency hints. Hints. We can just do case compare our relative frequency P of hints to rem of, and then what do we got? If it's greater than equal, this will be just easier with the, no, we don't need to compare. Just do an if statement. Then we recur, where we take the remainder minus the weight. Which I need to calculate. On P's, go to the next one. Else, we're gonna return here. Possible tile index, we're gonna turn P. Okay. Rand between is gonna be a little helper function. That's going to be a state, wave state, returning, and we got to give our bounds parameters. So it's going to be int, and between low and high, and generator. Wave state again, and then system.random is the function we need for that. Gen range no longer used. Uniform. all possible. Oh, no, uniform R for the provided range. Yeah. That's what I want. So we get our value, the X we want, and the next state of the generator. And we have to give that as a tuple of low, high. And return. Oh, then we got to put. We're going to modify. The state S, S, wave state gen equals gen prime. Then we can return our value X. Uniform R. What's the problem with this one? Oh, yeah, that's a pure function, sorry. Let this. Oh, and we have to give uniform R the generator. Here. There we go. Alright, cell total weight is a float. That's right. So we can either take the ceiling of it or the floor of it. No instance for random gen. Gen 8. Really? It says it should. What? You going silly on me, Haskell? What's going on? That can't be a thing. What's happening here? We're gonna add system.random. Ah, alright, we want to reload. Or do you want to restart? Yeah, there we go. We go here. Alright, let's add system.random. I'll just test this out a little bit on the REPL. So we want to do, let's make a standard generator. G, make standard gen. Let's see the value 500. Is that just a pure function? Okay, I guess so. And then uniform. Yeah. 3 is an int. 6 is an int. And G. Or uniform R, sorry. Yeah. It works totally fine. Does need to type int here. How high is an int? Turning an int, so we know we want that to be an int. That's so... okay, what the heck? Okay, this is a little strange to me. Is it the type that we chose for the generator? Is that the problem? Maybe it is. Maybe we want gen. Yeah, maybe that's the problem there. Okay. Now that's good, and we're cooking. All right. Whew. Okay, rem... Alright, that's just a name shadow binding. Yeah. Oh, missed one. Okay, sounds good. Care in that case, cool. Patterns here, that's the problem with that. Name shadowing issue. Okay, yeah. Let's call keys again. Okay, cool. And then all compiles. I don't think we have any remaining undefined. Oh, we have one remaining undefined. Possible patterns. We have to create this one in. No problem. This was pretty straightforward. We just want the indices. I think it's just plain old data.array. Pattern index. Yeah, the keys, the indices. Indices. Okay, cool. Still good. Okay. collapse at? Did we do it right? That's trickier to think about. So if we had a grid... I don't know if we can write a test for that. Let's see. Because all we're going to be doing here, when we do this and collapse it, is pick that one and know that we updated the state properly. Like, that seems trivial. We're also going to kind of get a random pattern too. What does it mean when we collapse that tile though? Well, it might be useful to pick to know that we at least don't go into our air bounds here. Things like that. So, yeah. Let's try something here. Describe collapse at. I don't know if we can write this test as a property, but we can, it's more like an example. I'm just gonna make sure we don't run into an edge case. Collapsing for some arbitrary grid doesn't matter. We need to be able to construct an example grid, though. We have a muck grid. We have to get the pattern result into in order to build it. So yeah, we will need some kind of texture as input in order to get the patterns from it, and blah 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 blah. Let's kind of make an empty texture. I think we have that. This is all our pre-processing stuff that's still kind of off to the side. We might want to like wrap up together. Muck texture. Okay, so context. Given a grid, and a arbitrary fixed texture. Give it a grid. It should collapse to a single pattern. There we go. So we can put our stuff up here for that. Test texture. We can make a texture. It's just a fill texture. We don't care about the patterns or anything like that. Like what the patterns are, just that one of them gets picked. So we'll pick one of a relatively decent size. Say 5. And then our pattern results. Patterns from our test texture of say 3 by 3. Okay, and then our grid should be grid with output size, so say 10 by 10, doesn't really matter, and our pattern result. Okay. So then we need a runner function for collapse at, since it's a state. Runway, maybe? Something like that. Of A to some monad of A. And that's going to be... Actually, we... I only care about the final grid. Yeah, so it should be... run eval state. We don't even need the monad grid. Alright, so then we combine that. Final state, eval exec state of the wave function. And we just want the final state dot wave state grid. Oh, no. Yeah, that should know that this is... Interesting. So this doesn't know, after running exec state, that this value here is a wave state? Oh, right, because we need the initial state, that's why. That's what's going on. Edit state. Okay. Still got a hole in the test. Yeah. Okay, so we can go to the spec code. So in the spec code now, we should be able to run wave with our wave state, set up collapse and all that. So we're gonna need our library. Our test library also needs random. Random here, and I don't think it needs MTL directly. But we'll need it because we'll need to make initialize that wave state. So call it in a wave state. And a wave state grid, wave state frequency. Hence, we'll need that, and wave state gen. That'll be like standard gen. We'll give it a fixed C to say 100. Okay, generating our frequency hints. We get from that pattern result. Okay, let's offer our pattern result. Frequency hints off of pattern result dot patterns. Pattern result dot pattern result patterns. What a mouthful. Okay, so then what happens here? Run wave, init wave state, collapse at. And we're going to collapse at, say, 0, 0. Resulting grid. Now the resulting grid cell at 0, 0 needs to be in a particular state. We could have a little function there to pull it out. That's basically what I'm thinking here. Almost based off of maybe at. Except we'll just pass in the grid and we'll do the unwrapping there. I'll put it after grid here. Cell at int. Or we can even do like this. 3D coordinate. Grid. Maybe cell. Clicks. Grid. Maybe at think actually maybe at, what did I do? No. That's fine. Yeah, what we'll do is we'll do grid. Maybe that. LX. But we have to unwrap the grid. Get cells. Yeah. Yep. So then we should be able to say cell at 0, 0 of our result grid of nothing. Well, that's a failure. But if we do get the cell, we should be able to say that the cell is collapsed. I think we defined that, if I'm not mistaken. We have cell collapsed. Or just collapsed. Yeah, there we go. Should be true. There we go. Let's see. What's missing? I think collapse at takes it as a tuple, like a, or yeah, that's all. That's all I'm doing. Silly me. 0, 0. Yep. That's test texture and import system.random. And some misuse of my own internal functions. Had a result. Takes a texture and a word, return. Yeah, that's right. Problem is 167. Oh, frequency hints isn't right? Okay. List a pattern of A. This might be like where record overloaded. Oh, do I not have overloaded record dot? I don't have overloaded record dot here. That's the problem. Overloaded record dot. I'm getting too comfortable with this language extension. Should probably just enable it everywhere. Cool. Survey says we're good. Okay, the problem with this test, though, possibly is our test texture. Since it is a fill texture, we're going to have a very even distribution of frequencies. They're all going to be the same. So it's okay-ish for now, because I got to end the stream. We're running out of time. I'm going to leave a little to-do in there, though, to make a little better test texture. Or we could turn this into a property test where we test with arbitrary textures. Oh, it just needs a type in for that one, does it? Alright, whatever. Yeah. That's what we'll do. Cool. Let's check that in. See how we did on our to-do list today. I think we kind of nailed that, yeah. Alright. Stage though, save, commit. Add, collapse, at. This function will collapse a cell in the grid at a particular index. Boom. Okay. Thanks for tuning in and watching this week. It's been fun. I hope you learned something or enjoyed yourself or just had a fun time chilling. Because, you know, we don't need to feel pressure to always be doing stuff or always be improving or using our time. However, if you just want to relax, just relax, man. It's all good. In that case, though, all the code that you've seen tonight is up here on GitHub. I'm Agent Ultra. My account on GitHub is Agent Ultra, and this is wave function collapse. So that's all here. You can check it out. I'll paste the link for you. And as mentioned earlier at the beginning of the stream, here in my socials, I'm on TypeStuffPL on Mastodon, and you get my profile there. It has links to all my other stuff, including my YouTube channel where I back up a lot of my video on demand. So if you want to watch these later, because you can't catch them all the time, that's where they'll be. And yeah, I do these streams once a week on Tuesday evenings, generally at 10 after 8 p.m. in the evenings in the Eastern Standard Time Zone. So you write that down, or if you like getting notifications about things here on Twitch, you know what to do there. Hopefully you have your notifications enabled. You can click on that little follow button. You'll get notified when I go online and stream. Because sometimes, occasionally, I do, once in a while, stream outside my usual schedule as the whimsy hits me. And otherwise, on YouTube, you can like and subscribe there. Helps the channel out and everything there. Of course, you can also go on the link above. The declarative.tv site there has a link to a Discord server where we have a channel for this stream as well. So if you're watching the VODs, you're catching up, or you just want to chill, there's a Discord server there. I'd be happy to hear about your projects, what you're up to, and those sorts of things. So hit me up there. And I think that's about all I got for this week. So thanks for tuning in again. It's been a pleasure. And may all your monads be free and your types always check. And we'll see you next week. Peace out. End of stream.